So the universe we live inside is close to a continuum. This is demonstrated by how I'm moving continuously across a stage. But the fact that I can move across a stage means that it's also mostly empty of particles, fermions in particular. That is the motivation for this talk. There are many interesting systems where the number of fermions are very much fewer than the number of places they can be. And if this lecture room were closed, the number of fermions would be fixed. This is called particle number symmetry. So this talk is about fermions living in a very big space, and you know that the number of fermions is fixed. There is not a superposition over many fermions. It is an eigenstate of fermion particle number. So why do we care so much about fermions? Generations of researchers have figured out many ways to make many interesting fermionic states. So if you think about quantum computing, for example, there are all these variational ansatzes to make quantum states. You can even make quantum ground states with phase estimation. Even in experiments, for instance, on optical lattices and atoms, you can also make very interesting fermion states. So what's common about all of this is that a lot of this is at low temperatures. At low temperatures, the number of fermions is more or less fixed. This is something that you know about the system. It is prior knowledge, and you should use it as much as possible. Suppose you've made, some interesting fermion state representing some interesting molecule or, some breakthrough problem. What do you do with it? Well, the natural thing to do is to measure it, because once you've made a state, measurement is the only next step. But how expensive is it to characterize a fermionic state? The simple answer, or maybe the most general answer, is that it depends on the dimension of your system. So if you're to do full state tomography on a dimension D quantum state, then more or less people know that it would take, polynomial in D samples of this state. You have to measure that many times in order to get estimates for all of the elements in the density matrix. If you could do that, you could reconstruct any observable that you cared to estimate for that quantum state. So if you think about fermions, N here is the number of places fermions can live in. It can be extremely large. In this case, because we have no constraint on the number of particles, the dimension of this is 2 to the n. So in other words, full state tomography on this thing would be exponential in n. That's pretty bad. Well, how about the assumption that we have only n particles? That helps a bit, but it doesn't help very much. You've gone from dimension 2 to the n to n choose m. That can still be an extremely large number. So, what is the simplification that lets us characterize fermionic states in a meaningful way? So, the key property is that most fermionic observables that we care to estimate, they actually are only supported by something that are called k-local fermionic operators, or in this case, k-RDMs. So what this means is that if you were to write any observable as a linear combination of number-conserving k-RDMs, number-conserving meaning that there are an equal number of fermionic creation and annihilation operators, the length of the product is going to be quite small, only 2k operators. And as examples of why this is useful, if you wanted to estimate interesting quantities like the energy for electronic structure, the Hamiltonian is a sum of 2 RDMs. Effective models for nuclear physics, 3 RDMs. Simpler things like dipole moment or density, 1 RDMs. And the case of Slater determinants mentioned in Kiana's talk, that would be the M RDM. For instance, if you have M electrons, then that's the M is the number of particles that goes into the K. So these are the fermionic properties satisfied by fermion operators. Kiana briefly went through an equivalent version based on Majoranas. And this is a defining property of what makes a fermion a fermion. So one of the major breakthroughs recently was this idea of classical shadows. And the reason why this result was so great is because it allowed us to characterize extremely large quantum states very, very efficiently. That framework, the original result was based on qubits, and we can draw an analogy between the qubit results, if you're familiar with them, with the fermion results. So in the case of fermions, you would say that m, the number of places fermions can be, well, that's n. And for qubits, n is also just the number of qubits. In the case of number of particles, well, for fermions, that's m. For qubits, there isn't really a strict analogy, but you could say there's a number of Pauli operators for each qubit. That's XYZ, that's 3. And then, just as how you can have k-local qubit operators for fermions, we have these KRDMs, which are short products of fermionic operators that are number conserving. So this number conserving property is important because we know that our fermionic system has a fixed number of particles. So the breakthrough in this Shadows paper is that we know that there are actually a huge number of k-local Pauli operators. You can just count them. 3 to the k, because for every qubit you can have one of 3 choices. And n choose k, because you can choose any subset of these, any size k subset of these n qubits. But it turns out that if you were to do local random basis measurements on these Pauli qubits, well, it turns out that the number of measurements you need to characterize any k-local Pauli operator, that number of measurements, number of samples of your quantum state, it doesn't scale with the size of your system n, it only scales with the locality of your operator. This is a super exponential speedup with respect to the size of your system. So if we have this result for qubits, then the natural question is there an analogous result for fermions? Well, surprisingly, there has not been. And there are a few ways to understand why this result has been elusive. The first reason is that, well, the technology for qubit shadows came first. So the natural thing to try is to map fermions to qubits. There are all sorts of ways to do this, as Jordan Wigner, there's Ravi Kitav, and many more. But the downside of these approaches is that if you map your fermions to qubits, you get long Pauli strings. In fact, just to hand wave back of the envelope calculation, the length of your Pauli strings is going to be logarithmic in the number of fermion modes. So if you just plug that into the k for k local, you get a scaling for the number of measurements needed to characterize all k RDMs as 2 to the n to the k. So you can see that there's the explicit dependence on system size n here. Some other work, they have tried more advanced techniques. For instance, Kiana talked about match gate circuits. You could think about what if you were to restrict your match gate circuits to also be match gate circuits that are number conserving. So that's work that was done by Zhao et al. But then what they found out is that this restriction means that your measurement channel is no longer invertible for these number conserving KRDMs. So something different is required. Match gate circuits that are number conserving and also intersecting the Clifford group. That's that result. So the result of this work is that we get the result that is in more or less full analogy to the qubit work. So you have a number of samples that you need, that is m choose k. If you have very, very few particles, but very, very many modes, places where your system can live, this gives you a very efficient way to characterize all of the KRDMs simultaneously. It's gone from n choose k to m choose k. And in the earlier example of how this lecture theater is mostly empty of particles, this assumption where number of particles is much fewer than modes is very natural to many systems. Although there are reasons why you might not always want to make this assumption. Depends on your application. So the summary of what this implies, how this improves prior work to, estimating of these KRDMs is just summarized here. For energy, before you would need, say, n squared samples, now you just need m squared. If you had, say, a basis set size in chemistry of 10,000 and 100 particles, you got yourself a 100 to the squared speed up. That's pretty good. And in the case of estimating these overlaps with Slater determinants, we've gone from square root n scaling to just constant scaling. So that's maybe super, super exponential in 2 parameters. So how does this algorithm work? The framework is more or less identical to the shadows framework. We just choose a different, distribution of, unitary transformations to randomize over. And here, the distribution we choose is that of these quantum match gate circuits, restricted to be number conserving. And how you can generate these is that you get an n by n hard random unitary. This is something that you sample classically on a classical computer, and would be the number of modes. And once you have this n by n high random unitary, you can use it to implement a basis transformation that is called the single particle basis transformation. So this is characterized by how it rotates a creation operator to a unitary combination of other creation operators. So in the case of Majoranas, this was orthogonal. Here it's unitary. And instead of having two n Majoran operators, you just have n. It's just a property of how you represent regular fermion operators rather than Majorana fermion operators. And one of the large benefits of choosing these match rate circuits is that there is an efficient quantum implementation of it. It takes only n squared nearest neighbor gates. Although I've referenced gates here, which implies I've made the choice of fermion to qubit model, this result is completely agnostic to how you map fermions to qubits. It works for any mapping, so it's quite general. You could do it in first quantization, if only you had a way to do this efficiently. So once you have applied this random single particle basis rotation, the next task is to measure it, just measure in the computational basis. And this pair, this choice of u, n by n u, unitary that you sampled, and the measurement result is something that you use to reconstruct your RDMs using an appropriate estimator. The estimator that we have here is also computationally efficient. It is quite closely related to Kiana's work, except that instead of having 1 degree of polynomial interpolation, you have 2 dimensions to account for particle number. But other than that, it's a related calculation. In this work here, we also managed to bound the average variance of all of these estimates. Although one caveat here is that we bound the average variance rather than the worst case variance across all of the KRDMs. This is due to how the math was difficult, and I'm sure somebody here could help fix that. So how does the proof work? Kiana went over the outline of how shadows work, so I'll briefly go through these again and point out the main differences. So this procedure of applying a basis transformation and measuring can be represented as a quantum channel. That's M of rho. Rho is your quantum state. In principle, if you could invert this measurement channel, then you would get your estimator for rho. That's the classical shadow. Once you have the classical shadow, you could in principle just compute a trace of this very big matrix, which you have classically computed, with any observable that you care to put inside, in this case, a KRDMs. But this, of course, would not necessarily be an efficient computation because rho hat, that's an exponentially big object. But supposing that you went through all of this and you had the estimator, then you could compute the variance of this estimator. In a lot of prior work, people talk about the number of samples you need to estimate all these observables to some constant error. But underlying these calculations is always this variance calculation, and then they use things like means of medians to convert a variance to an epsilon delta probability result. So what are the main differences here compared to prior work in fermionic shadows? So first, when you compute the twirling operator, the anti-commutation or anti-symmetry of fermionic operators is captured in how when you twirl your measurement result, this bit string that you got, you take the exterior product of this n by n unitary, the number of particle times. So when the number of particles is 1, this is a very well understood result. It is identical to just dimension D full state tomography. But it turns out that when you start looking at high exterior products, there haven't really been results out there that talk about what this evaluates to at all. And then how we managed to evaluate this is that we more or less took a brute force approach. Any product of unitaries, if you average over them on the high measure, can be represented in the basis of Weingarten functions. And then through some very complicated combinatorial arguments, you can count them and get the result for that operator that has some very neat symmetry based on symmetric polynomials of number operators. So once you have written this twirling channel in some closed form expression, the next step is to invert it. Inverting it means finding the eigenoperators of your measurement channel. And this turns out to also be symmetric polynomials of your number operators. So this property of all of these being symmetric polynomials of number operators lets you express this exponentially big object over polynomially few more abstract number operators. And when you estimate the KRDM using this, you get an estimator. This involves a lot of combinatorics as well. There's a lot of sums because of all of these complicated combinations of number operators. But it turns out that you get a triple hypergeometric sum that Mathematica cannot do. But a textbook called A equals to B by Wilf and Zielberger teaches you how. And to bound the variance of the estimate, well, you also get another sum. Now it's a quadruple hypergeometric sum, and the same textbook teaches you how to evaluate that. So we get the estimator and the bound for the variance in closed form. It's a pretty neat example. And if you were to upper bound all of those, you roughly get the results I claimed earlier, m choose k. That's the number of samples you need to estimate any KRDM if you know the number of particles. So in conclusion, one of the great benefits of this classical shadows framework is that it allows you to very compactly store a good representation, a faithful representation of your quantum state. If you wanted to characterize your quantum state, that would be 4 to the n numbers. You could do it, but then you couldn't store it for future generations. But what you can store is a shadow. The shadow is a very small object, n qubits, that's just n bits of data. That's great. It's not 4 to the n. You can do all your experiments today, you can do all your quantum computations, store the results, and if you forgot to compute something today, you can just pass it on to your grad students and say, you have this data set, go do that for me without spending money or time on running the experiment a second time. So, to summarize, for now the purposes of computing KRDMs or fermions, we can claim that we have a scaling that is independent of system size. It only depends on the number of fermions. This is an analogy to the qubit results, and I hope it's going to be very useful. The estimator is computationally efficient, so it's something that you can actually use in practice. I think it's optimal, but somebody here can also prove it. So, of course, this result is not perfect. It is quite common to investigate cases where your system is at half filling. I've made the motivation for how many interesting systems are at very low filling fractions, but there are good reasons to study half filling as well. We won't go into why. And for this result, we don't get as much speed up because, m choose k versus becomes n over 2 choose k compared to, the prior result set. It's not so great, but it's still a pretty good constant factor speed up. And the last caveat is that just due to the difficulty of evaluating this twirling channel, we could only do it for the twofold twirl. This gave us the average variance average across all the RDMs, but did not give us the worst case bound on each per RDM case. I did some numerical simulations on a bunch of states, and it tells me that there's maybe some constant factor difference between the two, average case and worst case, but that remains to be proven. So that's all for this talk.
All right. It takes a while. Okay, questions?
Thanks for the nice talk. Did you also look how robust this is if your initial state that you measure has some contributions that are in a different particle number space?
So what will happen is that you just get a linear combination of these things, although the estimator is dependent on particle number. Mm-hmm. So you'll get a mix.
So I think about you have a VQE and you want to prepare a state with a given number of fermions, but you don't quite get it.
That can only happen in a noisy computation.
Yeah. These two exist.
Well, we don't think about that. In any case, one of the benefits of this here is that because you know the particle number, you can always do error mitigation. Just measure your state and check that it has the right Hamming weight. If it's wrong, discard that result.
Oh, yeah. Yeah. Nice.
All right, there was another question over there somewhere. Oh, same question. Okay. Over there. To your right, yes.
Have you thought of instead averaging over the whole matchgate group? Is there a natural discrete subgroup one could do instead? And would that maybe simplify things?
So earlier on I mentioned that if you were to take the discrete version of the matchgate group and also restrict it to be number conserving, this turns out to not be informationally complete for this task. It doesn't let you reconstruct the KRDMs in its entirety. Is there a different restriction that is number conserving and also more discrete? Probably, but I do not know what it is.
All right, over there.
Yeah, so you write on the slide you think your results are probably optimal. Can you give any reason why you think they're probably optimal?
So this is more of an argument that works backwards. These randomized procedures, they are optimal for any given choice family of observables. You can always make a randomized distribution that is optimal for that thing. So if you go backwards, if you say that you have a result that works very well for this set of observables and it's randomized, it's probably optimal. It's not a great argument, but I think it's good enough for me.
Okay, thanks.
Right. There's another question over there.
Thank you very much for the very nice talk. So in quantum chemistry problems, I think there's many situations that we know that the ground state or the target state would be in specific point group symmetry or some spatial group symmetry. So in that case, I would expect that you would restrict the match gate groups. But do you think that that kind of restrictions, can you still construct the invert channel for the measurement? So my question is, if you know that there is some symmetry in the group state you have, can you also further restrict the match gate group?
So this would, I think, boil down to what are the KRDMs that you want to observe. If you know that your state is symmetry, then many of these KRDMs could have the same value. There will be a symmetry in these things. So in that case, you could certainly design, a randomization that would not allow you to distinguish between these KRDMs that give you the same numerical answer for that state. A general procedure to do this is not something that I can come up with right now, but I'm sure it could be done.
Thank you.
All right, there was another question over there.
Thank you very much for the impressive results. So is there a sense in which you can also do this for transition density matrices? So two different states, psi A and psi B?
Yeah, so a transition density matrix is just a KRDM. For instance, if you were to look at one state hopping to another state, where you change just one of the occupations, that's a one RDM.
But it's a sum over many RDMs.
Yeah, so in this case, you will estimate all the KRDMs in your transition matrix and add them together.
All right, over there. Oh, that's our first throw for today.
Okay. Hi. Thanks for the talk. So maybe just a small clarification. So when you say average variance, you mean averaging over all the KRDM?
That's right. So hypothetically, if to evaluate all of them, what would be the average error in any one of them?
I see. Okay.
Okay, I'm going to go with the last question. And there's a hand over there. Let's do that first.
In bosonic system, you would have a very similar algebra than fermion, just like commutators instead of anticommutators. Would your same methods also maybe work in bosonic systems?
Yes. This whole shadows framework will work for bosonic systems. You just have to define the right tooling operator. Maybe it could be your bosonic, quadratic, exponential. The challenge would be in evaluating the tooling channel.
All right, I'm going to do the last question. So what is stopping you from doing like a full sort of worst case variance bound? Like what's the technical issue somehow?
So because I use a combinatorial approach, the 2-12 required a lot of counting. With the 3-12, there's a lot more possibilities, and then I decided not to do it.
Oh, so this so this wasn't in the book, or?
Yeah, it wasn't in the book.
Yeah, okay. All right, with that, I think we're going to wrap up this session, so give a big hand.